Hi, everybody. Welcome to the second AFRICAST workshop. We are very excited to have you all here. My name is Bahman. I'm a professor at Cardiff University in the UK. And with Mitch, we are going to teach the workshop for the next 5 days. I will just give you a brief introduction of what we are going to do, and then I will hand over to Mitch for the first session today. First of all, you can see there are some functionalities here in Zoom. So there is a chat and Q&A and also a raise hand. Please use Q&A for any question you have related to the materials that we cover during the session. So we will make sure that we will keep an eye on Q&A, and if there is any question, either we will answer it live or we will type the answer there. So if you want to speak, please raise hand, use this functionality, and then we will unmute you, and you can also ask a question or provide comment if you like there. Now, regarding the mentorship, at the end of this training, that means on Friday afternoon, we are going to allocate you to mentors, depending on how many participants we have. We got this year 17 mentors from Cardiff University, but also from past participants of this workshop. So we will allocate mentors, and then we add you to the Slack channel, to the corresponding group, depending on how many groups we got. And then they will be in touch with you to organize sessions and help you with the exercises we have in the training. And I think that's it from me, so I'll hand over to Mitch. And if there is anything else that I forgot, please, Mitch, feel free to highlight as well.
Thank you,
Are you starting?
Go ahead.
Yep. Henry?
Oh, you're starting. Okay, sorry. So I don't know, but maybe we have a number of trainers, participants who have logged in more than once. Probably they could just be able to log in once, so that at least we don't have any disturbance on the background noise. Can you hear me?
Yeah, we can hear you. Yeah.
So hello everyone. This is Henry, and I hope we are all able to start without any challenges. And Bahman, Prof, I think we have a number of mentors around. So I know we are having, apart from the participants, we also have the mentors also joining us. So I don't know, maybe at a certain point we'll be able to actually just have them maybe joining us later on to help with the mentorship. Otherwise, I think you can start.
Yeah, the mentorship will start from next week.
Yes.
So there isn't going to be any mentorship this week. So we will start from next week, and we allocate students to mentors on Fridays. So you should be able to get an email on Fridays telling you this is the mentor, and also an email to join the Slack channel on Friday. But again, if you have any issue in joining Slack or any question about the mentorship, you can always send us an email as well.
Yeah, okay, thank you. So I think maybe Mitch can start, and thank you.
Great, thanks Bahman, thanks Henry. Hi everyone, it's great to have you all here, and I hope you're excited for a great week of forecasting. My name's Mitchell, I'm from Australia, so it's in the afternoon for me, so good morning to you all. I work at Monash University, I'm currently a PhD candidate, and one of the main contributions of relevance today is that I'm the developer of the software that we'll be using for forecasting. So if you've got any questions relating to the software or forecasting in general, it's a great opportunity for you to ask me directly. You're welcome to put any questions that you might have in the chat or the Q&A. I think Bahman mentioned that this is recorded, and we'll put the recordings as soon as we can on this Forecasting for Social Good AFRICAST website. So I'll put this in the chat as well. Everyone should have access to this through the emails already. But it's a good idea to have this website link up during the week as we work through these materials. And everything that you need to know about this workshop can be found on this website. So perhaps the most important here, we've got an introduction video that we've recommended that you all watch. This will give you an overview of how the website works and how this workshop as a whole will be structured and organized throughout the week. I'll leave that to your time to watch through that if you haven't already. And on the schedule page here, at the very top, you've got the link to the schedule. So you can see this is organized into 5 different days of materials. And today we'll be looking at the basics of what a time series is, and also how to visualize time series patterns and data sets. So we want to be able to understand the data before we're able to model it and make some forecasts, which we'll do in future weeks. Okay, so to start, here's our instructor information. If you have any questions, you can ask them directly in this chat, of course, or you can reach out to us via email. You can find our information here. But we can't do this alone. So we're fortunate enough to have the excellent volunteer help from many mentors, some of which were participants in the AFRICAST workshop in the previous year, the first year that we've run it. And we're hoping that in future years, that perhaps some of you would like to take on the role as a mentor and continue being involved in the AFRICAST program, spreading the knowledge of forecasting further. So there's so many mentors this year because we've got so many participants. I couldn't fit them all on one slide. So here's the rest of the mentors here. So thank you everyone for volunteering. Thank you to those mentors. And as mentioned, you'll meet with your mentor in a small group of participants next week to discuss the topics that we discussed this week, but also work through some hands-on exercises relating to a real data set from Africa. So you'll have some hands-on experience actually producing forecasts from time series statistical models. You'll practice playing around with the data, transforming it and visualizing it. So this is a good opportunity for you to put into practice the skills that you'll learn in the webinars with Bahman and I. We also have some great support from the coordination and admin team. Perhaps Bahman could talk a little bit about that relationship, or Henry, perhaps?
Well, I can very briefly say a huge thank you to Henry and the team. Basically, this relationship started with an in-person training that I delivered in Nairobi in January 2023. Again, this is actually a part of an initiative called Democratizing Forecasting Forecasting for Social Good Committee at the International Institute of Forecasters. We also deliver in-person training in some countries. So next year, I think there is a training maybe in Zambia. It's not confirmed yet, but Mitch has been delivering in-person training. I deliver in-person training in many countries, actually in East Africa in particular. And then we just discussed with Henry that we could start a new initiative with an online training, and Henry has committed to this project and coordinated all the activities, advertising, receiving applications, dealing with all this. So a huge thanks to Henry and the team. But if you want to add more, Henry, please feel free to add more.
Okay, thank you, Bahman. So we do have some assumptions, some prior skills that we expect you to have. On the website, you would have found a recommendation, if you aren't familiar with R, to try out the Learn R materials. So down here on the main website, you can see preparation. We do assume that you have some familiarity writing some R code, especially using the tidyverse packages. So these packages will be used a lot with the forecasting tools that we're learning this week. So some familiarity with how to use dplyr in order to transform your data set, ggplot in order to visualize it. That will be really helpful in order to follow along and participate in the exercises this week. If you aren't familiar with that, there's a self-directed website for learning R. I'll put that link in the chat as well. It's also available on that workshop website, of course. And here you can pick and choose the topics that you aren't less comfortable with, and you can get further practice in that for the rest of the week. So we're also going to assume a little bit of familiarity with some basic statistics. We assume that you know about the mean and standard deviation, indications of the average and the spread of data. We're also going to be using distributions when we produce forecasts. Specifically, we'll be using the normal distribution or the Gaussian distribution. And in order to optimize parameters, we'll use maximum likelihood. Now, if you're not so familiar with these concepts, that's okay. You'll still be able to write the code and produce the forecasts. But to get a deeper understanding into what these forecasts are and how the models are actually working, it would be useful to have some familiarity with some statistics. But because we've got such little time this week, we're not going to go into the details of how these models work in a statistical sense. We'll give you all of the tools that you need to use them in a practical sense. So everything that you need to apply these data sets or these models to real data sets and produce forecasts to solve real problems. As a result, we're not going to spend much time on the theory and the inner workings of how these models work. We're instead going to focus on how to apply these forecasting skills to change the world. Now, there is an excellent textbook, which is also free and available online. This is the Forecasting Principles and Practices textbook. The third edition is what we'll be using because this uses the latest software that we'll be using this week. And you can get free access to this textbook online at otex.org/FPP3. So yet again, I will link that to you in the chat. So here's the website with my professors, and this goes through all of the details, the statistics and the theory that we won't be covering for time purposes in this workshop today. But if you wanted to learn more about the models and the techniques that we're learning this week, this textbook is an excellent reference for looking deeper into these methods. And at the end of each chapter here, there's a collection of exercises as well, so you can get some practice. More practice on the material is available in this textbook. Now, you would have seen that we ask you to install the FPP3 package, and I noticed that there's a few questions relating to installing this. We'll address that shortly. It looks like a very specific problem to your internet connection, perhaps. But the FPP3 textbook also comes with the FPP3R package. So if you haven't yet installed the FPP3 package, you should be able to run library FPP3 if you have installed it. If that doesn't work, you should try install.packages FPP3. Now there's a lot of code that this needs to install, so it will take some time if you haven't already done it. So if you haven't yet opened up R and installed the FPP3 package, I recommend you try starting that now so that by the time we start working on some examples that I want you to follow along with, you'll have this software ready to go. Okay, there's another reference here. Bahman, would you like to talk about this reference?
Yeah, so this is a book that is also online and available for free. I put the link in the chat as well. This is a more like a high-level introduction to forecasting, and it is written in a way that is more like tailored to those that are new to the area of forecasting, or to professionals or executives or sort of like managers. Maybe they're not really involved in modeling or in a way producing the forecast, but more they are like users of forecast. So they are working with forecasting teams, let's say, or data analysts, and they need forecasting to inform decisions or their activities. So this is more useful for this. So if you are already familiar with the forecasting, it is okay, but it's still, there are some chapters that you might find really interesting that goes beyond also the professionals or executives. I will put the link here in the chat as well. So you can also read some chapters of this book if you like.
So here's this book here. And this is with Stefan and Enno, who are also great demand forecasters. They work a lot in practice, putting these techniques into industry applications. So lots of great examples in this book as well. Also free and available online, which is excellent. Okay, the last thing here is the International Institute of Forecasters, and this organization is the main organization for forecasting around the world. And in fact, they've sponsored this workshop and the more general, the Forecasting for Social Good initiative. So this is the institute that has made everything this week possible, and they will be providing some certificates of participation for taking part in the AFRICAST workshop. So this is a great recognition of the skills that you will learn this week. And in order to get this certificate, you'll need to attend all of the lectures and participate in all of the exercise sessions with your mentors in order to get this certificate. So the Forecasting for Social Good Committee is sponsored or supported by the Institute of Forecasters. And I recommend that you follow us on LinkedIn and Twitter. And if you do post on social media, in order to follow along all of the activity with AFRICAST and the Forecasting for Social Good initiative in general, please try to use these hashtags as well. Then we can see what you're posting about for this workshop.
Mitch,
Bahman, what's your role with the Forecasting for Social Good?
Yeah, just one thing that I want to highlight here. Well, I was the founder of Forecasting for Social Good Committee. So, but now I passed the chair to Michael Porter, who is associate professor at the University of Virginia. So, who's currently chairing the Forecasting for Social Good Committee. I think one thing I wanted to highlight that is relevant to you, I think, participants, is we have developed a small grant called Forecasting for Social Good grant. It is $5,000. So we provide this grant to researchers in developing countries. They have to work with an international collaborator as a co-applicant, let's say, and also with a local, national, or international organization, like it could be an NGO, it could be governmental organizations, and so on. So if you are interested, please check it out. I'm not sure when is the deadline for this year, but I think you can also, fill in an application and submit it. And you can, use this money to advance your project, or you may use it to attend, let's say, international conferences and expand your network in the area of forecasting. I'll try to put the link to the grant there as well in the chat.
Excellent. Thank you, Bahman, and thank you for all your work with getting the Forecasting for Social Good program off the ground. It's an excellent program to have. Okay, I'm not sure if we can do a poll here. Have we got polls set up, Bahman?
Don't think actually there is a poll. No, yeah. Well, there is a poll.
That's okay.
If you click on more, there is a poll quizzes there. Do you see that?
I don't have access to that. No, maybe you do.
It seems like
Otherwise, we can just write in the chat.
Yeah,
Okay, we'll just use the webinar chat box for this. Now, the first question here is just to gauge your familiarity with R as a language. Maybe you've used R to solve other modeling problems before, and you wanted to start using it for time series and forecasting as well. So this first question is ranking your familiarity with R and R programming. So for example, you might be a guru, you might have the R core team, that's the people that have wrote R itself, and maybe they're coming to you for suggestions on how to write some R code. Possibly not. Maybe you're an expert and you've written several packages on CRAN already. Or maybe you're just a user. Maybe you use it sometimes and you take some time to learn how to use a new package or how to find the right function. Or maybe you have no idea what R is. Maybe you're thinking we're speaking like pirates when we keep going like R this, R that. So 1 through 8, I want you all to put a number in the webinar chat and I'll scan through it to see roughly how familiar everyone is with R as a language.
I just set up one poll. I don't know whether it will work, but
are you able to launch the poll? I'm not seeing it anywhere. Oh, excellent. So Bahman's figured it out how to create a poll for this webinar, so you can just fill in the poll directly in Zoom. And if I bring that across, Bahman, can you see the results of the poll on the shared screen? Excellent. Okay, who's the guru? I need to know. Maybe I have a few R questions that I need some help with.
Yeah, there is one for now.
Okay, we're seeing a very nice distribution here. Looks a little bit log normal, a long right tail. Okay, I think that's almost everyone. So thank you so much for answering that. It looks like most of you are comfortable with R, use it quite often, and are comfortable using it, while a few of you are users and it still takes some time to figure out the right function. So that's perfect. It's good to see that everyone knows R and has at least used it or downloaded it before, and that most of you have enough familiarity to follow along with this course quite comfortably. If you're in the beginner or maybe even the learner category, I recommend you having a closer look at the Learn R materials that I linked to you before. It's also available on the website, just to brush up your skills with data manipulation using the tidyverse. We'll be using that a lot today and a little bit more throughout the rest of the week. Bahman, where would you put yourself in this poll?
Is a good question. I think I wouldn't definitely put myself as guru. I think, yeah, between skilled, maybe an expert, I would say.
Yeah, I think I'd put myself pretty firmly in the expert category. I've written several packages which are published on CRAN. I poke around with the internals of R occasionally, but I haven't had the R core team ask me for any advice yet. Maybe on some forecasting they'll ask me someday. There's a few problems with the base time series software included with R itself, and that's why we're using some additional packages in order to make our lives more easy for forecasting. Would you be able to restart that poll, Bahman? The options have changed slightly. We've just removed one of the categories.
Yep. Let me see.
But this next poll is about how experienced you are with forecasting specifically. So this isn't necessarily forecasting in R, it's just time series in general. So have you thought about time series before? Have you made a forecast perhaps, be it in Python, Excel, some other software? How familiar are you with forecasting?
Just give me 1 minute, I think. There is
That's
no
okay.
Copying, I think, at least I don't know.
Might have to create the poll again. So the options here, we've got Guru. I wrote the book and have done it for decades, and now I do the conference circuit, all the way down to what is forecasting? Is that where we get the weather forecasts from? And I get this question a lot. So a lot of people, of course, don't know much about forecasting at all. So perhaps I'm talking to someone about my work and I say, I'm a forecaster, I predict the future. And everyone thinks that I'm talking about the weather. It blows people's minds. It really surprises them that you can forecast more than weather. But of course, forecasting is so useful when it comes to understanding a business and what might happen next, or planning around government changes and budgeting. So a lot of the examples we'll see throughout this workshop are applications in business and in government. Okay, so we can see Bahman has opened the poll now, and it looks like many of you are answering it very quickly, which is great to see. Thank you for taking part. Bahman, where would you put yourself?
Well, I think forecasting is one of my main area of interest. So I'm more interested in conceptual, let's say, philosophical, but also applications in healthcare and humanitarian supply chain. So again, I can is something between skilled and expert, I would say.
I think you're being too modest. He wrote the book. So remember this book here, Demand Forecasting for Executives and Professionals. This is Bahman's book. So I think he's being a bit modest. I'd put him much higher than skilled for sure.
There is actually
me personally,
a new book coming
yeah,
out in forecasting for healthcare as well, hopefully in about 2 years' time. We are writing it at the moment. So it's forecasting and operational research for healthcare management. It's more like application.
So Bahman's definitely too modest. He's definitely in the guru category. I see him at the conferences every year when we can. I put myself in the expert category. I've not yet written a book. I am working on one, but it has been my main job for about a decade now. So I would put myself in the expert. It's good to see that there's a lot to learn for most people here. We're looking at the poll. Most of you are in the learner category, so you're still learning about forecasting. You might have heard about it a little bit and have even tried it out yourself, but not many of you are skilled or comfortable. Not many people have produced forecasts for themselves very often. So this is exactly what we wanted to see from these polls. We can see that everyone has enough familiarity with R as a language and coding to follow along, and everyone needs to learn a lot more about forecasting, which I hope by the end of this week, you'll be more in the comfortable, if not skilled categories with the quick start workshops that we're giving you this week. Okay, in addition to the FPP3 package, there are a few other packages that you will need to have available. These are the Tidyverse, galley, Sugar Ants, and ASTSA. So I will write some code for you in the chat as well if you haven't already got them. I don't know if we need the Tidyverse, but it's a good idea to have that anyway. Oh, I hope my microphone wasn't off for that long. Bahman, what did I say last?
Well, it was just maybe off for 2-3
moment?
2-3 seconds.
Okay. I'm not sure why that turned off. It's probably a shortcut. So I suppose you've heard about installing the packages. That's excellent. The outline of this workshop very closely follows the FPP3 textbook. And you can see the relevant chapters from that textbook on the right here. So we're going to start with the time series data and time series visualization, which is all in chapter 2 of the book. And then in the following weeks, you'll see that we're pretty much going to work through the entire forecasting principles and practices textbook. And one last time, you can see the workshop URL here for everything that we're looking at this week. I'll put that in the chat. So we're now 30 minutes in, which we're right on time. We've started at 8 a.m. UK time. We've got another hour until we take a 15-minute break. And then we've got another hour and a half for the second seminar lecture. And then lastly, you'll organize a time for your group with your mentor for the mentorship sessions in the following week. Anything else you'd like to add to that, Bahman, before we get into the forecasting?
No, Mitch. Thank you.
Excellent. Okay, so our first session here is on the basics of what is a time series and how do we look at time series data using code and using R specifically. So we're going to start with what is forecasting. Now, in a statistical sense, forecasting is using a model in order to summarize the behavior of the past. That's what we have in the black line here. We're collecting all of the information that was available right at the time we're making the forecast, which is this red dashed line. And then we're trying to replicate that pattern that we saw in the past into the future. So we're trying to produce a similar shape into the future, essentially. Now it's very faint here. Perhaps that could be darker, but there is a line here which looks like the data afterwards. So you can sort of draw a forecast yourself. If you just visualize something that would look reasonable into the future, what are you expecting to see? Would you expect it to be a flat line? Something like this? Well, that doesn't match the historical data at all. The past doesn't look like this line at all. What if we had a flat line down here? Well, the center of the data, the mean, is roughly around 450. So if I had the forecast being much lower than that, that's not a very good forecast as well. What we do see is this up and down pattern that is repeating every year. So in the future, we would expect a similar up and down pattern in our forecasts. And in this first day, we're going to understand what that pattern is and how we might visualize that in order to understand exactly when this peak is and when this trough is. And so that we understand this, then we can think about how we would use a model in order to summarize this repeating up and down pattern in order to produce forecasts into the future using the similar pattern. So what do we need in order to produce a forecast? There's quite a few things that we need. Most importantly, of course, we need the data. We need data from the past that we intend to predict the future of. So if I wanted to forecast the future population, I need some history, some previous values of population, so that I can look at the patterns that currently happen, and we assume that those patterns will continue into the future. Additionally, you might think about using other information in order to forecast population. Perhaps you're using GDP or income. Then you would need the historical data and future data, importantly, of those predictors. Of course, if we're predicting population, we don't need the future values of population itself. But if we're forecasting population using GDP, then future values of population, when we're forecasting them, we'll also need to know the future values of GDP. And that can pose a problem for forecasting that we'll see in a couple of days' time when we talk about regression modeling. But fortunately, most of our time series patterns are functions of, or can be summarized with functions of time itself, such as trends and seasonalities that we'll learn about today. In this case, we don't need any deterministic predictors or regressors, although it can be useful and improve your accuracy of your forecasts if you're able to get these extra information from other predictors. Now, you might also have other stochastic processes and predictors that might affect your forecast, And if you consider them when producing a forecast, you'll also need data about that as well. Now, the last entry here is expert knowledge. So it's really useful, especially when you're forecasting things that we don't know a lot about or don't have a lot of history about, historical data, where the models aren't very good at summarizing the past. This is when it can be really useful to bring in experts that know a lot about this industry, a lot about this pattern, that probably know more about the problem than your data can summarize. And in this case, you might bring in these experts and any additional contextual information that they have in order to adjust the forecasts that you're producing, or add these future possible values of GDP and deterministic predictors. So these can help you provide the new information when it's not available. So one of the questions here, which is perhaps one of the first questions you should ask when producing a forecast, is why? Why do we need to make a forecast? Have a think to yourself. If you've been in a forecasting situation where you've been asked to produce predictions about the future, maybe you're predicting the future revenue for a company or the future population for an area, why is that information important to forecast? And while you think about that, I'll answer a few questions. So one question here is, how far into the future can we go with our forecasts? Now, this really depends on the predictability of the past data. Something like population is often easily predictable. Here, I'm just drawing a time plot that we'll see in the second session. So we might have y on the y-axis, or in this case, population. And then very often we'll put t, or time, on the x-axis. And population generally looks like a smooth line going upwards. Now, because this line doesn't have many random variation, it's very easy to produce a forecast for this. And the forecast for this will be very accurate because it's not very random for the historical data. For a data set like this, we can forecast very far into the future. If our data set was instead maybe revenue, and we were selling a product, so maybe this is sales, let's say, and our product was new and not many people knew about it, it got really popular, and then it fell off popularity and people stopped buying it. What's going to happen next? This is much harder to predict because we don't know when it will be popular again or if it will ever be popular again. So in this case, our forecasts might be like this, but we'll have very wide uncertainty around it. And in this case, if we forecast very far into the future, we essentially won't know what the actual value is. We'll just have uselessly wide intervals. They're not entirely useful. They just say that we don't know enough about this data set or this pattern in order to accurately forecast far into the future. So it's a great question. How far in the future can we forecast? And the answer is it depends, unfortunately. It depends on how complex the data is to forecast. Another good question here, you might have used prediction when you're talking about regression models or other cross-sectional models in the past. Forecasting is similar to predictions. The only difference here is that we're predicting the future. And it's a very specific type of prediction because what happens in the future depends on the past. When we use prediction, you might predict any value, any person, and their likelihood to default on a loan or something. You might predict their age. A forecast is a prediction about time, and more specifically, beyond the future. So now we're into an extrapolation problem, which causes some added complexity. And what is the difference between forecasting and prediction? I think I've summarized that quite well. A prediction is usually from a regression style model or a cross-sectional model where you can predict a specific thing from a observation. And that is irrespective of time. It doesn't matter what time it is in the future, the past, whereas a forecast is specific to predicting something over time and predicting the future. So another great question there. Bahman, if you could dump all the links in the chat again, that would be appreciated. Okay, so hopefully you've had some time to think about why we produce a forecast. Now, there's many reasons why you might want to produce a forecast, but most importantly, your forecasts need to have a purpose. They need to derive a decision that actually impacts the company or the government or the plans. If you're just producing a forecast to draw a line on a screen, then there's no point making that forecast. So here's some useful questions that you might ask when you consider if and why you need to use a forecast. Maybe you're building a new hospital and you wanted to decide if it's needed or not. Are there going to be enough people in this area in 10 years' time? Maybe you wanted to forecast the population of that town and see if that population will grow enough such that the other hospitals nearby are not large enough to support that population, and therefore we need to build a new one. You might also forecast the numbers of injuries in that area and see if injuries are growing as well. Now, this is a business application. Maybe you're running a call center and you're trying to plan how many people need to be answering calls for the next week. So in this case, you might be forecasting the number of calls that the call center processes and how many calls a staff member can process, and see if the number of staff that you're rostering on for next week are sufficient to meet the number of calls. And if there's not, you might want to bring in some more staff for the call center. Now, this last one was, of course, a very influential one in the past few years. How many doses of vaccines were required next month? Now, I did quite a lot of work in the past 4 years with the Australian government, producing forecasts for the number of infections for the COVID-19 pandemic. Now, they were, of course, very concerned about hospital beds. Do we have enough space in our hospitals to take care of the sick, the people that were infected with COVID-19? And more so, they weren't worried about how many doses of vaccines, they were worried about how quickly we can vaccinate the entire population. So they were very interested in seeing when our population will have a vaccination rate of 90%, because that was helping them decide when some of the restrictions on mobility can be eased so that people can return to their normal work and normal day of life. So these questions that we're trying to answer using forecasting were absolutely critical for the government and its decision making. It allowed them to decide exactly how limited the population needs to be to prevent the hospitals from being overrun with patients from COVID-19. And it also helped them plan and support industries like tourism to understand when tourists will return to Australia after the COVID-19 pandemic. They wanted to know when things would go back to normal and also how much it would cost in lost revenue for the tourism agency. So overall, forecasting is critical for decision making. It helps inform decisions by understanding what might happen next. And lastly, it helps provide evidence for these decisions. When you're a government and you're deciding to make a new hospital, the general public will want to know, why do we need a new hospital? Why do we want to spend our tax money on a new hospital? It's useful to provide evidence that if we didn't build a new hospital, then we wouldn't have enough hospital capacity for the population, the growing population. Now, to produce a forecast, there's generally a few steps that you would go through. Now, the first one we've been talking about is identify if we need a forecast in the first place. What sort of questions are we asking that need answering by a forecast? And then we need to determine the requirements. So what sort of data do we need? Maybe we think about the types of models that would be relevant and appropriate for that problem. What is the variable that we're trying to predict in order to inform and answer this decision that is being made? Once you've identified the question and the model or the data required to answer that question, you of course would then go out and collect the data, gather the data and information, tidy it up, prepare the data, which we'll be doing today, and visualize the data to understand the patterns that exist, so that when we specify a model, we capture all of the patterns that exist in the data. So today we'll be focusing on these three sections. I guess we've already covered these first two. So already in the first day, we're going to be covering most of this forecasting workflow. Now, of course, when we come to choosing and training models, there'll be a lot of options for us to consider, and that's what will represent the bulk of the next few days of the workshop, understanding the different options available to us for modeling. Okay, so let's think about preparing the data now. We're going to assume that the data has already been gathered. So the time series packages that we'll be using in this workshop for representing time series data and producing forecasts and plots of the data are these packages here. And these packages can all be loaded with a single command, which is library fpp3. You can see when I ran that code, it attached a whole collection of packages, including the Sybil package, which we'll be using for time series data. It loaded the Sybil data package, which is some example data sets that we'll be using in our exercises, along with feasts for visualizing the data and fable for producing forecasts. And there's a few other tidyverse associated packages that we'll be using to manipulate the data today as well. Here's some examples of different data sets that we might consider forecasting. And these are all data sets that I've forecasted in the past. Now, there's one type of time series here. Each of these examples are changing by one factor. Can anyone suggest in the chat what is different about each of these time series? Yes, everyone's right. So you're all mentioning the time. Some people are mentioning the period, duration, and time intervals. Now you're getting more precise. A few people suggesting seasonality. Yes, some of these will be seasonal, some of them won't be, but some of these will both have seasonality. So it's not unique to the time series. Everyone's right when you're thinking about time and time periods. So we call this the frequency. So write that out here. The frequency of the time series is how often we observe an observation from this data set. So the Olympics, of course, run roughly every 4 years. So when I prepare this data set, I might set it up with a 4-year frequency. The time index will go from 2000 and then 4 years later to 2004 and then to 2008. And that's a great word in the chat there, resolution. So it's how much detail we have in the time series, and it's resolution in time, how fine grained the detail is for the data over time. So next we might have profits, and we might report that annually. We might also report that every day or every minute, depending on how you might be working with the data. One example we'll see a bit this week is the quarterly data sets, specifically Australian production. One such thing Australia makes, of course, is beer. So we'll look at that time series and how to forecast it. But you can also forecast things that are much more frequent than quarterly and annual data. So you might have daily stock prices or hourly demand for electricity. When you're trying to plan around a hospital and you're trying to make sure that there are enough spaces in that hospital for all of the sick people, it doesn't matter if there was enough space on a daily level if in 1 hour there wasn't enough space. So often for more important things where every moment matters, you're considering a more frequent time series in order to answer that problem. Now, of course, you can get down to 5 minute, even down to the second or millisecond with exact times of a transaction. Now, often when you get down to this frequency, you might not need that precision, that amount of granularity, that resolution in time. And you might consider aggregating it up into a less frequent example. Maybe you're looking at daily transactions instead of every transaction in the dataset. Okay, so here's the packages that we'll be using today and for the rest of the week. They're all written out here, but you don't need to load each of them separately. All you need to do is write library FPP3. So now's a good opportunity, I think, for you all to open up R. You can use RStudio if you like, and try to run library FPP3. Earlier, I told you to install it if you haven't already, so you don't need to install it again if you already have it, but just try to run library FPP3 and see if it works. You should get this message attaching all of the packages. Now, there was one question in the chat where you had trouble installing FPP3, and it looked like you might have problems accessing the CRAN servers for downloading packages. Another option you might consider is the WebR environment. So I'll put this in the chat. This is useful if and only if your RStudio isn't working with loading FPP3. In the WebR website, you can load in FPP3 directly, and it will ask if you wanted to install it. So I'll type 1 to install this. Then it should download all the packages that you need directly in the web browser, and you should be able to follow along for today. But if you're still having trouble installing in your own R website, in your own R installation, perhaps reach out to your mentor and ask for further help with that. Okay, has anyone tried that out? And if you've got any problems using RStudio with FPP3 package, try out the WebR, and if neither of them work, let me know. We'll try to get that fixed for you. So I've just put the WebR link in the chat. So if you're having trouble using RStudio with the FPP3 package, do try out the WebR platform. It usually works a bit more often, but the downside is that everything you do here is temporary. So you can, of course, click the Save button up here in order to save your work or copy it across into a separate file when you're done. But this is a temporary R session just for experimenting, really, which is good for us learning today if you have problems installing it. But it's a good idea to have R installed properly for the rest of the workshop. You'll find it easier to use. Okay, we're going to continue here. It doesn't seem like there's any other questions, but if you do have problems installing it, do let me know in the chat, and hopefully one of us can answer it. Okay, let's have a look at a time series dataset. So this is the global economy dataset. It's included in this Sybil data package, this one here. And if I open this in R, I can just type global economy after running library FPP3. Then you should see a table-like output. If you've seen a tibble before or a data frame, it's very similar. We'll see the differences shortly. Try that out. There is a question in chat, error in install packages, FPP3 not found. If you have this problem, it's because you haven't put quotes around this. If you've got object not found, you'll need to put these quotes around FPP3. If anyone else is having problems installing the package, you'll need to give me a little bit more information, what sort of error you're getting, and maybe I can help you with it. Yes, perfect. Thank you, Victor, for copying that across. That's very helpful. Okay, so what makes this data set, global economy, a Sybil? So in addition to a normal data set that you might be working with in R, a Sybil knows about the time aspect of the data set. So it's a time series tibble, that's the TS for time series, and the tibble is a data frame that you often use in R. Now, this Sybil is aware of time itself. So you can see it knows that the frequency, remember when we're talking about the different dataset examples? The 1Y here indicates that we have an annual frequency. Every 1 year, we get a new observation. And if I check the year column, you can see it counts from 1961, 62, 63. It counts up by year, one after the other. So that's a good thing to check when you're working with a time series dataset. Make sure it's got the correct frequency that you expected. Additionally, we have this key variable, which here is country. Now, it's not possible to observe things like population and have different values at the same point in time. If I told you that today is 2024 and the population is 8 billion, and then in another line of the data set, it's also 2024 and the population is 3 billion. This isn't possible. We can't have two separate points in time, two separate observations, two separate populations at the exact same point in time. But it is possible to say that the population of the world in 2024 was 8 billion, and the population of Asia in 2024 was 3 billion. Now we're measuring the population of different places, and we've got different time series. So we call this the key variable. This is the index variable, the time, and this is the measured variable, the thing that we're measuring or forecasting. And you can see in this data set, global economy, the key variable is country. And in the square brackets here, it tells you exactly how many countries there are. In fact, it tells you how many time series overall this data set has. So there's a total of 263 different time series of population, GDP, and imports and exports over time in this data set. So you can see there's quite a lot of data here. We're working with 15,000 rows across 6 columns. And we're going to try and forecast all of them throughout this week, among many other data sets. Okay, there's a few other questions about installing. So this one here about cannot open compressed file, no such file or directory. This I recommend you use the WebR platform today. So Jacob, with your error here, it seems a bit too complicated to solve right now. Maybe you can ask by email or work with your mentor would be the best option for future classes. But for today, I recommend trying out the WebR platform. It should work there. Hassan sees that the dataset has 15,150 rows. Oh, sorry, I misspoke. Of course, it has 9 columns. It's not 6 columns. How do I get the dataset? To load the dataset, you'll need to first run library fpp3 and then use global economy. So if you write global economy and go Control Enter, I think it might be Command Enter on a Mac. I'm not sure. You'll have to try. But if you go Control Enter, or you can highlight the code that you want to run and click Run up here, then you'll be able to see your dataset. Excellent. Ahmed also asks that your dataset opens with additional variables like growth CPI and it has missing values. So in this case, I just had my screen a bit too small. So when I make my screen a bit bigger, you'll see growth and CPI are also in this dataset and they're filled with missing values. This is just because Afghanistan in the year 1960 and 1962, they didn't report what their growth rate and their CPI was. But for other countries, perhaps if I look at Australia, so I can write some dplyr code here, country equals Australia. You can see that the growth was available in 1961, 1962, and so on. So other countries reported different data set, different values over time. Okay, let's have a closer look at what these key variables are and what the indexes are. So the index variable is time. So whichever variable describes the time of the observations. So when did this GDP, when was that GDP measured for Afghanistan? It was measured in 1960. So the index column, in this case year, will tell you which column represents time. And that's what is used to calculate the time series frequency of 1 year here. It's looked at this dataset column and it's seen that it increments by 1. And therefore the frequency is 1 year. Next is our key variable. Our key variable here is country. You can see that written at the top. And the key variable identifies a time series. If I didn't have the Afghanistan country column in the dataset, then later on in this dataset, I would also have 1960 GDP of Australia, say, and the imports was, well, maybe the GDP, I don't know what GDP would be here, maybe it's a few trillion. The population of Australia is 27 million. Now, if I didn't use the Australian column and the Afghanistan column, then for the year 1960, I would have 2 values in the dataset and 2 different populations. Population of Afghanistan being 9 million, and the population of Australia in 1960 was probably more like 16 million. That's a bit of a guess. I have no idea what it was. We could find that out. But the key variable makes it possible to have multiple different countries, multiple time series at the same time in the same data set. And lastly, we have our measured variables. You don't need to specify which variables are your measured variables. It's just everything that isn't an index and a key. But the measured variables are perhaps the most important because that's the thing that we're looking to predict. So when we make a plot of the data, we're always plotting one of these measured variables. When we're forecasting, we're always forecasting one of these measured variables. There's another question in the chat here. Global economy, unexpected symbol. As Joseph suggests, you'll need an underscore between global and economy. In R, we can't have spaces between variable names. Okay, so here's another example. It's tourism. And this is the number of people coming to Australia every quarter for tourism purposes. Now, I want you to write in the chat which of these variables is our index variable, which has the time information. The code for filtering out Australia, I'll put that in the chat for whoever has asked for that. Yep, seems like everyone has the right idea. The correct answer for that is the quarter column. Now, it does happen to be quarterly data, but that isn't necessarily why we've called this quarter. I could have called this time. I could have called this anything. What is the frequency of this data? So quarter is index. Okay, I get some mixed opinions. I have 1 quarter, 1 year, 3 months, every 3 months, Yep, seems like people are starting to get the right idea. You can tell what frequency the data is by looking at the top here. So here we have 1Q, which means 1 quarter, which is exactly the same as 3 months. So both of you, everyone that wrote 1 quarter or 3 months is correct. Sorry, yes, 3 months in a quarter, yeah. And you can see that here in the time column, we are still in the same year, 1998, but we're going from quarter 1, quarter 2, 3, and 4. So it's not a yearly frequency. If it was a yearly frequency, it would go from 1998 directly to 1999. And that's what we saw in the previous example on the global economy. See how it went up by 1 year at a time, 60, 61, 62, and the frequency here was 1Y, 1 year. For the tourism data set, we observe it more often, in fact, every quarter. So quarter 1, 2, 3, 4, and then we move on to the next year, quarter 1, 2, 3, 4, and repeating. So therefore we have 1Q. Now, what are the key variables in this time series? Perhaps you can write that out in the chat as well. Which variables uniquely identify the time series? And how many of those time series are there? Okay, lots of different answers here. I'll give you a clue. It's possible to have multiple key variables. You can have multiple different columns which are used together to uniquely identify a time series. Okay, very good. Seems like people are starting to get the right idea. In fact, the Sybil object here is very nice to you. It actually tells you what the key variables are. So it's telling you that the key variables of this data set, because we've already set this up, is region, state, and purpose. But normally when you get a data set, you'll need to tell R and Sybil package which variables correspond to the index and which variables correspond to the key variables. A good trick for this is usually the key variables have a character type. They're usually just text, which describes which type of time series it is. So in this case, for the region, it's Adelaide. So if I draw a very rough map of Australia, Adelaide is about here. Can't forget Tasmania. And Adelaide is in the state of South Australia. So the state of South Australia looks like this. But there's also more than just location. So in the previous data set, we saw different countries. This time we're getting a bit more specific, where in the country of Australia, in the state of South Australia, in the region of Adelaide, so we're getting very fine detail in location, but we've also got an additional reason, additional identifying variable for the time series, and that's purpose. Why did they come to Australia for tourism? And that in this case could be for business, for leisure, for going on holiday, for seeing friends and family, or for some other reasons. So there's 4 different purposes of coming to Australia in this data set. Overall, we have 304 different time series in this data set. So yet again, we have a lot of data. Now, here we have 24,000 rows and 5 columns. You can count out those columns here. We have 1, 2, 3, 4, 5 different columns in this data set. This is just a summary of the overall data set and doesn't tell you much about the index and the key variables. The index, the frequency is shown here, and the key, the number of time series, is shown here. Now, lastly, we have our measured variable, trips, and that's the number of people that have come to Australia for each region, state, and purpose. And this is the thing that we're interested in forecasting. So yet again, index, the key variables now are 3 different variables in this data set, and our measured variable is trips. So the Sybil dataset that we've been looking at before works very similar to a regular data frame in R. And in fact, all of the same tools work as well. So you might have used dplyr before in order to filter the time series. You can do the same thing for tourism. So how to access this dataset? Oops, this one here. If you've loaded the FPP3 package, you should just be able to write tourism in order to see this dataset. And then you might filter the purpose to be a holiday. And now we get all of the people traveling to Australia for holidays. And you can see there's now 76 different time series in this dataset because we're no longer looking at the business and friends and other reasons why people might come to Australia. We're just looking at holiday travel. We'll be using the filter function quite a lot throughout the week in order to prepare our dataset for forecasting. Okay, do we have any questions about index variables and key variables? There's one question in the chat. Does 304 time series mean 304 combinations? That's right. So it's not based on the time index. It's just based on the number of combinations of region, state, and purpose. So there's 4 reasons people might travel, 4 purposes. I think there was 76 regions in states, and 4 times 76 is equal to 304 different time series in our dataset. Okay, let's try to create a Sybil for ourselves from scratch because you're not often going to be working with a data set like tourism, which is already set up with the key and index variables. Often you'll be given a data frame or a CSV or a data set somewhere else, maybe an Excel file. And then when you bring it into R, you'll need to convert it into a Sybil. You'll need to say which variables are the index variables and which variables are the keys. So here's an example of creating a Sybil. Now here we have a direct way of constructing a Sybil ourselves using data. So I've said the years 2012 to 2016, given it some observations Y, and now I need to say which of these 2 columns, year or Y, which of these columns is my time index. So I say the index is equal to year. That's how I say that the year column is where time is. And you can see that the frequency of this data set has been correctly calculated as every year, 1Y. So that's one way that you could create a Sybil, but we don't use this approach very often because usually we have a data set already from the client or the government. So you usually import a data set and then convert it into a Sybil rather than creating a Sybil directly from scratch. We'll come back to that. Okay, we'll do this in a slightly different order, but we're going to look at the number of prisoners in Australia now. So maybe we're forecasting, the purpose of this might be forecasting if we need to build another prison, or maybe we need to hire more prison staff. So we can load in this data set using read CSV. So I'll do that now. I'll put this in the chat as well, but I'll change it a little bit so that it works for you. Where did we put the prison dataset, Bahman?
Good question.
I could probably get it from materials. Okay.
Can't see it from exercises. I think no, it's not demo.
I will see if I can
It is in
get this link
materials.
for you as well.
The materials data.
I might not be able to share this one with everyone. I think you'll just have to watch for this one. And I will send this data set out as an exercise. I think we can manage that, but you can try this out afterwards. There's another question, can we get the code? Can we get the slides at the end of the session? You can get everything on the website here. So if you go to the schedule, you can see we're currently on day 1 in the first session. So if you click on this link here, you will see all of the slides that we're working through. So here you can copy all the code. You can try it out for yourself using these slides. Okay, so normally when you create a Sybil, you'll be getting it from a data set, and you'll usually start with a data frame or a Sybil. That's a great link. Thank you, Bahman. We can all follow along. I will use that. I forgot that we had it on GitHub. So there's the data set. We'll get the raw version of this, and I will convert this into a direct link. It's a lot of code, but this should work for everyone. So if you copy this code that I've just put in the chat and try to run this for yourself, you should have the Prison dataset loaded directly from the web. And this is very common when you're working on a real project. Often they'll give you a CSV or an Excel file, and they might just give you a website that you can download it from. Here's how you can take that link on the web and load it into R for us to prepare and plot with Sybil and time series patterns, time series packages. Okay, so the first step here, yes, Bahman?
Sorry, Mitch, just wanted to also reiterate, if you go to the website, there is a link called download, and you can download all materials from there as well if you like. So everything, it will download all the materials that you need and accessible in the website, or you can also use the GitHub link that is there as well if you like, if you use GitHub.
That's right.
But sorry, this website at the moment is for the version we delivered in 2023. So this will be updated next week slightly, with the live coding and, the videos, but the slides, exercises, everything will be the same. So slight changes, but you'll see these changes hopefully from early next week.
Yes, I have made some of those changes, but for the later workshops, we'll be making some more changes. So make sure you keep up to date with the website. What you download today, I don't think will be changing. I think we've finished all of the slides for this year's materials. Okay, so hopefully you've been able to run that code that I put in the chat. I'll put it in once more in case you haven't got that. And if you run that in R, then you should have access to the Prison dataset. And we want to convert this into a Sybil. So you might have used this as function before, as data frame, as numeric. We've got a function for converting a data frame into a Sybil called as_Sybil. Now, if I run this, it doesn't work. And this isn't because I've written bad code. It's because you haven't yet told me what variable is the index column and which variable is the key column. And it does its best to guess. It's guessed that the date column here is the index. And that's correct. The date column contains the time variables. But it doesn't yet know what the key variables are. And as a result, we have duplicate observations at the same point in time. You can see in 2005, March 1st, this first point in time, we have 0 prisoners. And then in 2005, March 1st, we have 2 prisoners. We can't have 2 different values at the exact same point in time. Therefore, we need to include some key variables. What are the key variables for this time series? Maybe you can put some in the chat. Which of these variables do you think are the key variables? Okay, very good. So it seems like people are getting the right idea now. Some of you are just mentioning one of them. There's actually 4 different key variables in this time series. I did see a couple of mentions of date as the key variable. That's incorrect. Date here is the time variable, the time index. So we start by writing the index is equal to date. We say which column here is corresponding to the time variable, and that's the date column. And then we say which variables are my key variables. So key equals, and then I've got multiple different key variables. So like other things in R, we put them together using the C function, combine multiple key variables into the same key. So here we have state, gender, legal, and indigenous. And when I run this code, we now get a tibble. So we've successfully converted my tibble into a time series tibble, a tibble, and with this we can produce some plots and later analysis. But there's a problem. Can anyone identify the problem with this time series? There's some zeros. That's actually not a problem because it is possible for no people to be in prison, especially when you get very specific with ACT, like a very small state in Australia, female remanded, ATSI. There's a chance that no one that meets all of those criteria is 0. Lucas, if I look at more of the count variable, you'll see that some of them are more than 0 or 1. So if I print n equals maybe 100, you can see some of the observations are 9, 7. We have more data. It's just for different time series. Yeah, I see a few people starting to clue into the time frequency. The interval is not correct. You can see the interval here is 1 day, but what is the gap between each of these time observations? This is all one time series. All of the key variables match up that I've highlighted here. It's not 3 days. This is in year, month, day format. So the days is the very right column here. That's right. So the time interval here, the frequency, should be 3 months instead of 1 day. Why do you think we've got 1 day here? I mean, to us, we can see quite obviously it's 3 months apart. Is the software not very clever? Now, the reason for this is because each month has a different number of days. So when we go from 1 day to another, or 3 months to another, sometimes there might be 90 days, other times there might be 89 days, or 91, 92. So there's different numbers of days, and therefore there's an inconsistent amount of days in between them, and the best we can do is 1 day. Here's the code in the chat for everyone that wants to catch up. If you're having trouble running this code, I suggest you try copying what I've just put in the chat and try it again. And then you can see if there's any difference in the code that might be why you're having an error. So the problem here is that this is a daily time index. You see it goes down to the daily frequency, but our data set, here's the code, I put it in the chat. Our data set is actually quarterly. So we need to set this as a quarterly frequency. And the way in which we do that is using time functions. So there's these special time functions that we can use to set up annual data. Oh, I am sending it to the wrong chat. Sorry, everybody. Now I understand why everyone's had trouble accessing the code. My apologies. Hopefully everyone can see that and try for yourself now. I was sending it to the wrong person. Okay, so the problem here is that we need to convert our time index, instead of being daily, which we currently have, we need to convert it into quarterly. And we can use dplyr to do this. We can use the mutate function. So maybe you've seen mutate before. If I mutate my date column and I wrap it up in year quarter, this will convert my date into a quarterly frequency. So it can see that March 1st, 2005 is quarter one of 2005. Now, it's nice to give this a good name, so maybe I'll call this quarter. And then I want to convert this into a symbol with the quarterly time index. So what is my index now? I've got a choice. I could use either the date column or the quarter column. Alfonso, if you right click, if you highlight the code that you want to copy, like this, and then you right click copy, that should work. So we need to choose if we want a date or quarter, if we want to use this representation or this one. So when we set the index, I'm now going to use the quarterly frequency. And I'm going to use the same key variables as I had before. Just move that down a bit. So now you can see my time index here is my quarterly variable, and I now get the correct frequency from that variable. And that's a good thing to check. Is there some way to send the code in a way that can be copied, Bahman? Do you know? Seems like people are having some trouble.
Well, I can copy the code, so...
You can copy the code? Okay, yeah. Maybe for future workshops, future seminars tomorrow, maybe try updating Zoom. But I'll put all of this code online once we're finished today, so that you can go back and try it all out for yourself.
I think you haven't, maybe if you have copied something else and you didn't copy, that's why you get material, data, praise, and whatever. I think if you just select, what Mitch put in the chat and click right on it, or press Control and C and copy, it should work. That's what I did.
So you can see the code for this is also available in the slides. You will need to update this URL so that it grabs it from the internet. But other than that, you can see that we set the quarter variable to use the year quarter type. And then we use the as_sybil function with my new index, my quarterly index, and the key variables in order to get my sybil with quarterly data and 64 different time series. Okay, there's another example here for the Australian Pharmaceutical Benefits Scheme. There's a lot of Australian examples. I apologize, I'm Australian. And this data set we'll just very briefly go through. It's another opportunity for practice with indexes and keys. And this data set is available directly in R as the PBS data set. So if you're having trouble loading in the prison data set from the CSV, the PBS data set will allow you to do it directly from the loaded packages. So you just type PBS into R. What is the frequency of this data set? Remember, the frequency is how often these time series observations happen. Excellent, everyone's got that right. You can see that we've got the 1M here saying it's 1 month. And you can also see in the time column, month, it goes July, August, September, October. And this was done using the year month function. So if I go back to this slide here, this slide is very useful for you. To get a monthly frequency like we saw in that, we use the year month function. So if you're creating a monthly data set from scratch, like we did with the prison example, you would use the year month function instead of year quarter. Now, of course, like we saw before, you can use the filter function to pull out a specific time series, in this case, a drug classification, A10. And then you can remove the unnecessary columns that you don't need. So we can use select to further tidy up the data. This is all tidyverse skills that is covered in the Learn R materials. So if this is new to you, I recommend, again, that you try out this Learn R website. So you can do that between today and tomorrow. We'll be using that more in future classes. Now you might also, this is particularly useful, is to summarize the data. Maybe you want to add up variables over time. So in order to get the total cost of the A10 medication, regardless of the type of concession and payment, then we can summarize the sum of cost. Again, this is all covered in the Learn R website. You might convert it to millions with mutate. Hopefully you've seen some of these functions before, and you can see that this also can be used for time series. The difference here is that when we did summarize, it automatically grouped by the time index. A time series will never want to ignore or forget about time. So when we try to summarize things or calculate over time, it will implicitly group by time. It'll always keep the time variable around. Okay, with that, we're going to take a break for about 15 minutes. We'll come back at 10:45, I believe. Is that the right time zone, Bahman? 9:45? Perhaps it's safer if you say that.
Well, that's why I'm in Paris as well, so I was a bit confused. Yeah, it's 9:45, yeah, UK time. Yep.
It's on the website, 9:45. So we'll take a break until 9:45. During this break, if you have any questions, feel free to ask them in the chat, and I'll do my best to answer them. And then when we come back, we'll look at visualizing data to look at the patterns of trend and seasonality.
Shall I pause the recording?
What was that, Bahman?
Shall I pause the recording or just leave it as it is?
It can be paused. I'll do my best to remember to turn it on. We neglected to mention this at the start, but I'll be teaching the first 5 of these seminar sessions, and then for the last 5, Bahman will take over. So on Wednesday, you'll have the both of us. We'll teach 1 session each, and that's how we'll be splitting up the seminars throughout the workshop. Okay, thank you, Bahman. Welcome to the second session, which is now that we have our time series data, we need to be able to look at it and visualize it in order to understand the patterns that might exist in it. So when I looked at that line at the start, and it went a bit like this, we had this time series with a lot of up and down patterns. This is about visualizing this data set in different ways. And I talked about how we had y on the y-axis, t on the x-axis, time. And this is the most common type of plot that we often work with. In fact, it's called a time plot because it's so commonly used to visualize time. But this isn't the only style of plot that we might use. We also have plots specific to looking at seasonality. And we also have plots for looking at correlations, which is some subtle differences, subtle patterns that you might see in the data. So there's a lot to get through in the second session, but it's nice and visual and fun as well. So here are some of the patterns that we often associate with time series. And we've seen one of them already. The up and down pattern that I was talking about is known as seasonality. It's a repeating pattern with a fixed period of time. We'll have a closer look at that later. You also have the time series level. A level is approximately like an intercept. You probably have seen or heard of an intercept from time series from regression models before. A level is very similar to an intercept, except it can change over time. So the level of a time series, maybe we talked about the example where I talked about sales. The level of the time series at the first point in time might be here, L1. In the middle, when it got really popular at time 2, we might have a different level, L2. And then finally at the end, time 3, we might have a different level here. Now the level is changing over time. If I did this with a regression model without the time series part, it would just be a flat intercept, just a flat line. But because we're working in time series and things are able to change over time, the level of the data is roughly the center of the pattern. So it's able to change over time. Now you've probably heard of trends before. A trend is something going up or down. And you might have local trends as well. It might go up and then down. So here we have an increasing trend, and then later we have a decreasing trend. All of these consistent increases or decreases are known as trend. Now, autocorrelation is slight similarities from one day to the next, which is a bit harder to think about intuitively, but we'll look at that with a specialized plot in order to see if there's any pattern at all. And lastly, we might have things that are completely unpredictable. You might have heard of these as noise before. And this is really important, not because it's an interesting pattern in time series, but later on when we make some models, we want to find that the model has captured everything that exists, all of the patterns, and whatever is left over is hopefully just noise. There's nothing left over. And lastly, we might have exogenous information, so additional information, predictors, that might relate to the observation, the data that we're forecasting. And this is very similar to what you usually use in a regression cross-sectional problem. So here are the definitions. I'm not going to spend too much time on this because we've talked about them more broadly, but there is one that I have not mentioned, which is a cyclical pattern. A cyclical pattern looks very, very similar to a seasonal pattern. It has the same up and down pattern, but there's a difference between them. And I'll have a quiz as well for you to try out, seasonal or cyclical. A seasonal pattern has a fixed period of time. It's always consistent. Whereas a cyclical pattern does not have a fixed period. So often it's at least a couple of years, but the time between the pattern repeating changes every time the pattern happens. So it's less consistent. Visually, they look very similar, but when you look closely, there are some differences that are important to consider when modeling. So here is the level. Now, these two are actually the exact same level. The level of the data in the dashed line on the left plot is 100, and the level of the data in the right plot is also 100. Now, in this case, the level is fixed because the data doesn't have any trend. But if the data was trended, maybe this data went up and then down, then the level, the dashed line, this one here, the dashed line would follow it very closely. The level is allowed to change over time. Here is a trend. So this plot on the left has an increasing trend. Now the data itself doesn't look like it's increasing very much. It can be a bit tricky to see these, but the one on the right is a bit more obvious. So you can see the decreasing pattern of the data is consistent over time, and therefore we have a decreasing trend. Now here's that up and down pattern that we saw in the first session, and this one is seasonal. We can tell that it's seasonal because every pattern is exactly the same size in time. If you count them up, there is 1, 2, 3, 4 observations in every pattern. 1, 2, 3, 4, 1, 2, 3, 4. So because the number of observations in each pattern is the same, and the shape of the pattern is similar from pattern to pattern, we call this seasonality. And seasonality is very predictable. Seasonality happens for a lot of reasons, often relating to the weather. So if it's cold, people might use more electricity to heat their home. If it's comfortable, people use less electricity. If it's really hot, people might use more electricity to cool their home. So often seasonality is related to weather. It might also be related to daylight. So of course, people work during the day and sleep during the night. So more people are awake and walking around the cities during the day. More people are using a website during the day. And most people aren't doing anything during the night when they're sleeping. You might also have business patterns here. People go into work at 9 a.m. and go home at 5 p.m. That's a very common business pattern that you might see in sub-daily data. So you can have seasonality with lots of different frequencies. Periodicity is what we call it. In this case, we have quarterly data, and that explains why every pattern has 4 observations, because this is a yearly seasonal pattern. Every year or every 4 quarters, the pattern repeats. Now we can combine both of these patterns together. So now we have an up and down pattern every 4 quarters, which is my annual seasonal pattern. And I've got a trend, an upward trend. So I'm going to call my trend T and my seasonality S, and my data set is equal to some combination of T and S. Now we can combine trend and seasonality in multiple ways. You can do it additively or multiplicatively. On the left, we've just added them together, but on the right, we have multiplied them together. Can you see the difference? Just visually, what is the difference in the data? That's the dots here with the lines connecting them. What's the difference between the one on the left, additive, and the one on the right, multiplicative? And while you think about that and write it in the chat, another good question here, is noise the same as random fluctuations? Yes, you can consider random and noise to be the same thing. Okay, we're touching on the idea. A few people are saying slope. They both have slopes, and yes, it looks like they have different slopes, but that's not the main difference. The scaling is different as well, 140, 200, but not the main difference that I'm thinking of. The left has the same variance over time, and the right has diverging variance. That's exactly what I'm looking at. So the additive one, you see the variation is constant, whereas the one on the right, the variation is increasing. Now that's happening because the trend is added to the seasonality, so the variation in the seasonality is always the same, whereas here it is multiplied on the right. So if my trend, if I'm at a very low level, if my data is small, and I multiply my seasonality by a small number, I'm going to get a small seasonality. That's why my variance is smaller. But when the level is larger at the end of the time series, then I'm multiplying my seasonality by a big number. And so the amplitude or the variation of my seasonality is going to get bigger. So very often you'll see one of these two patterns in the data, an additive seasonality or a multiplicative seasonality. And it's very useful for when we model the data to know if we have an additive or a multiplicative pattern. Later in the course, when we look at exponential smoothing, I believe that's on day 4, we'll find a model that can handle both additive and multiplicative seasonal patterns. Okay, so this is an example of a cycle. How is this different from seasonality? You can see that this has both cyclical patterns and seasonal patterns. This repeating up and down pattern here happens every 4 quarters. So the small up and down pattern is seasonal. But with these dashed vertical lines, I'm identifying a cycle. The cycles in this pattern are increasing and then drop sharply. Increasing, drop sharply. Increasing and drops. See how this is a longer pattern? But what makes it cyclical is the inconsistency. As pointed in the chat, it's irregular. So maybe the difference between these two observations is maybe 9 years. But you can see the next cycle is longer. Maybe it's 11 years. And then we have a really short one, 8 years. A cyclical pattern has inconsistent duration. You can also see that the pattern is slightly different as well. In the first cycle in the data, you can see it goes up for a bit, and then down is spread over like 3 years. It goes down for a while, whereas the next time it goes up for a while, but drops very sharply in less than a year. So the shape is slightly different, but what you can expect from a cycle is that at some point it's going to increase and then drop again. Exactly how it increases and how it drops isn't very easy to predict. So seasonality is very easy to forecast far into the future, whereas cycles are very unpredictable and not very easy to forecast. But a cycle like this is very common. This is actually from cement production in Australia, and this is relating to a business cycle, the booms and busts of the economy. And we expect that the economy to grow and suddenly collapse, and that cycle will repeat into the future. Exactly when it collapses is a lot harder to predict. Okay, so far we've been looking at time plots, and we can create some time plots ourselves in R. So I'm going to copy this code. I'll put it in the chat for you as well. Hopefully someone can put this in the question and answer. Apparently some people are having more, finding it easier to copy code from the Q&A. I'm not sure if that's the case. But we're going to bring this into R. And you can see we're looking at the Ansett dataset. Ansett is an airline in Australia, or it was. It went out of business, and that's why we can use the data today. This was an old consulting project for my professor. And you can see that it has a weekly frequency. So every week we have the number of passengers. We have the airport route that the flight was on, and then the class of the travel. In this case, business, but there's also economy and premium. So if I filter one specific time series in this dataset, the Melbourne to Sydney route on the economy class, and then we use the autoplot function, we get a time plot of the passengers column. So there's a few things going on there. We have our dataset. We do some data manipulation to narrow down what we want to look at. And then to make a time plot, we use the autoplot function, and we specify which of the measured variables, in this case is only one, that we want to produce a plot of. What can you tell me about this time plot? Just visually, what has happened to the number of passengers flying economy from Melbourne to Sydney? Is there anything strange that you can see? Celestine, for this code in the link on GitHub, this one, I've lost it, this one here, I'll update this at the end of each session. It's not realistic for me to update this as we go. Okay, lots of good ideas here. A lot of people have identified the change in trend. So it's fairly flat here, maybe decreasing a bit, but definitely after the year 1990, the trend seems to be increasing. But you can see that there's a lot of random stuff going on. There's a lot of noise. So there's this unexplained drop in several places of the time series. But there's also this really strange drop here. Why has there been no people flying between Melbourne to Sydney? Yeah, there's some ideas. That could be a typo. Maybe there's some data quality problems. So this would be a good opportunity to ask whoever gave you the data, hey, I plotted the data and I saw this is really strange. What's happening here? And then they might give you an explanation. So this isn't actually a mistake. This is real data and this actually happened. The airline stopped. That's exactly right. So here there was a strike. All of the employees refused to fly. So the airline ground to a halt. So there were no flights for the Ansett airline in that year or those few weeks during the strike. There's also a strange drop here. It didn't quite drop to 0, but it's a big drop, and it seemed to revert back to normal slightly after. So let's have a look at what that might be. So if I plot this data, but instead of looking at a single time series, now I'm going to look at all of the different classes of travel. So I'm going to look at just the Melbourne to Sydney route. And now you can see during the strike, all business, economy, and first class travel was 0. There were no flights in the air. But what happened for the second strange change is that economy went down and was replaced with business. And this is because the company decided to make business cheaper and economy more expensive. So they tried to play around with the value of different classes, and that's why the total number of passengers in each time series has changed substantially. And this poses a difficult problem for forecasting. But regardless, being able to see the data like this and describe the patterns, a decreasing trend here, increasing trend, a strike with zero flights, a class change, being able to tell the story of the data set is really valuable for better understanding the data and what might happen in the future. Okay, another time series here. We can just look at the slide for this one. What patterns can you see in this data set? Maybe you can type them in the chat. Dennis, if you could ask your question in the chat, that would be excellent. That's excellent. So I see someone suggesting that there's multiplicative seasonality. I was going to ask, I was seeing if anyone found that. So that's right. We have an increasing trend. It's not quite linear. It's got this curve to it. So it's a growing anti-diabetic drug sales. But it's also seasonal. We can tell that it's seasonal because we have this very consistent pattern, and this pattern repeats every year. So it's the same period of time, 1 year, between each pattern repeating. But more than that, have a look at the variation. This is a multiplicative relationship. We have the trend times the seasonality, because when the trend is small or the level is small, we're multiplying the seasonality by a small number, so we get a small variation. But at the end, when the trend is large or the level is high, trend times seasonality is multiplying by a big number. So I get a bigger fluctuation. So I end up with this cone shape of growing variance in the time series. Can everyone see that? I think most people have got the right idea. There were a few suggestions that there could be some cyclical patterns. There wouldn't be that much cyclical patterns in this data set. There could be a slight amount of cyclical patterns, but it's not something I would consider for a model. A lot of the other things that exist in the data set is the random variation. So you can see the bumps year to year. These are unpredictable. They change every year. Sometimes it's smooth, sometimes it's bumpy. So this has trend, multiplicative seasonality, and noise, or random variation. They're the three main patterns that exist in this data set. Okay, to look at the code, here we've taken our PBS dataset. We looked at this one in the last session. Just give me a moment to get switched back here so I can copy it. I'll run this through line by line for you. Okay, we start with our PBS dataset that we saw in the last session. This has lots of different types of drugs and types of support available. It's a monthly time series. And here I'm just focusing on the A10 classification, which is anti-diabetic drugs. Now, I don't mind, this gives me 4 different time series for co-payments, concessional, general, and safety net. So there's a few different options here. But I'm not worried about the details. I just want to see the total cost of anti-diabetic drugs. So I'm going to use the summarize function from dplyr, again in the Learn R materials, to add up the total cost for the A10 drug. And then, like we saw before with the ANSET dataset, I'm using autoplot to create a time plot of the cost variable. The rest of the code here is adding a label for the y and x-axes and adding a title to the plot. Does that help you understand the code? It might take some time reading through it, but I think it's useful to go step by step and see what each step has done in order to produce the result. Okay, let's have a look at a different type of plot now. So we're looking at seasonal plots. Now, as you might expect, a seasonal plot is better at looking at seasonality. And this is useful to tell the difference between seasonal patterns and cyclical patterns. So here is a time plot. This is again the amount of beer produced in Australia every quarter. So you can see it's a quarterly data set here. What patterns can you see in this data set? You put them in the chat when you think you've got the answer. And also, is it additive or multiplicative seasonality? Yeah, great. I think everyone's got the right idea. It's very difficult to see if this is additive or multiplicative, and that's because it has a decreasing trend, but it doesn't decrease by much. So if it was additive or multiplicative, it's hard to see because we're multiplying, if it was multiplicative, we're multiplying by a similar number the entire time. So this has a decreasing trend, very slightly decreasing trend, and it has seasonality because we have a consistent pattern with a consistent gap between them. But it's hard to see if it's additive or multiplicative. I think both is reasonable to say here. Without further information, I think additive is reasonable. Simple models tend to give better results, and additive patterns are simpler. Now, this is the exact same data set, but plotted in a different way. If we were to look at this visualization, this time plot, and I asked you, what time is it in this peak? Is it quarter 1? Maybe it's quarter 3. What time corresponds to the peak and what corresponds to the trough? It's very difficult to see with a time plot to see the shape of the seasonal pattern. But if I split this data set up into seasons, so I break it up, and then with each of these small sections that I've drawn, I plot them on top of each other now. That's exactly what a season plot is. So you can see on the x-axis, instead of time, I now have time within seasonality. So only the time between those patterns that I was drawing out before. And this makes it very easy to see what has the maximum production, the peak of the seasonal pattern, and what has the minimum. Okay, so to answer the question before in the chat, Q1, 2, 3, or 4, which has the maximum beer production? Perfect. So everyone can see that the line goes up to Q4 and that the beer production is maximum in Q4. Roughly, what is the beer production in Q4? So if I'm in Q4, I've got these values. What is the amount of beer made in Q4? So we can read that across. And we can see it's in 475, 500, around that range. Of course, it changes from year to year. So we get a whole range of different values that we usually get for beer production in Q4. What is the minimum beer production? Which quarter does that exist in? And what is the amount of beer produced? So we call this the trough. The trough is the minimum, the peak is the maximum. So great, it seems everyone thinks that it is in Q2, and that would be right. Q3 is also very similar. So usually I'd say Q2 and Q3, because there's not that substantial of a difference. And reading it off, you're right, it's 400 or thereabouts. It changes from year to year. So the season plot is the exact same as the auto plot that we saw before. See how we used auto plot here for the beer data? To create a season plot, we use gg_season. And that will automatically look for the seasonality and plot it. And this is useful in order to see where the peak and the trough is. What quarter or time within seasonality corresponds to the minimum and the maximum demand. Okay, here's another data set, again from Australia, from my hometown in Melbourne. So this is the amount of electricity demanded in Australia. What is the frequency of this data set? The frequency, again, is how often we observe time. That's right. So we have a 30-minute frequency. You can see again in the square brackets here, 30 minutes. And because it's a sub-daily time series, because we're more frequent than a day, we need to consider time zones because there's daylight savings times. So it's 30 minutes in the Australian Melbourne time zone. That's a lot of data. You can see we've got 52,000 rows, but that corresponds to just 3 years of data. There are 52,608 30-minute periods in 3 years of time. It adds up really quickly. Now, I can understand why you might be confused with it being 1 day, because there is a date column here, but this is just provided for your convenience. You can use it to plot the data, you can use it to summarize the data, but the actual time index is the lowest frequency of the data, which in this case is the time column. You see it goes from midnight, 30 minutes past, 1 hour, 1:30, 2 o'clock, 2:30. It's a 30-minute increment. And there's two variables that we might like to predict. We've got demand and temperature. Here is the ggseason function on the Victorian electricity data. What can you tell me about the demand of electricity over time? Another question here. What variable is holiday? So you've seen that I have ignored this column. This is another measured variable. And this is more useful for predicting. So people use more electricity when they're working in the office or in the factory. And when it's a holiday, people aren't working. So electricity demand actually goes down. So this is one of our predictor variables that we might like to use in a model in a later day. So the index variable is time. A tricky question, what is the key variable? So this is the index. What's the key variables of this data set? Okay, some mixed opinions. It's a tricky question because there are no key variables in this time series. There's no key variables because there's no need to identify multiple time series. There's only one time series in this data set. And that's why I don't have a row of the output saying key and the number of time series. There's only one time series. So in this case, we don't have any key variables for this data set. All of these variables here are measured variables. That's a tricky one. Okay, so onto the season plot. This is the seasonality over the year. What can you see? Just visually, you don't have to be clever about it. Maybe there's an increasing pattern, decreasing pattern, more variation. Maybe there's nothing going on. You could say that there's no seasonality. What can you see in this plot? Okay, there's a few good ideas there. Most of you have picked up the seasonality. If you're looking for a trend in this plot, it's probably not the right plot to look at. A trend is better to use a time plot to see, an auto plot. A season plot is really only good for looking at seasonality. You can see other patterns, but it's much easier to see seasonality. Now you can see that there's a lot of variation. We'll look at that later. But you can see broadly, there's an increase in July. Why do you think more people would use electricity in July? Excellent. So when I ask this question in America, they get very confused because they often forget about the hemispheres and they think this is lovely weather, middle of summer. No, this is freezing. It's cold. So people use more electricity to warm their home. So the cold is more stable, it's consistent. What about in summer? What about the increase here? It is hot. But the difference here in Australia, when it's hot, it's not consistently hot. We'll have really hot days and then really nice days. So the pattern here in January is a lot more unpredictable. It's a lot more random. And that very closely relates to one of my predictor variables included in this data set, temperature. We'll see a plot of that later. Now, what about all of the variation that happens for the entire time series? This data set has more than just annual seasonality. There's more patterns that happen over a fixed period of time than just every year. What about every week? So if I use the ggseason function and specify a different seasonality, in this case I'm setting the weekly seasonality, instead of showing the year, January to December, on the x-axis. Now I'm showing the day of the week, Monday through Sunday. What can you see in this plot? You can see a lot of patterns in this one actually, but over the week, what is the main changes? Okay, Betsy's got the right answer. So weekdays, Monday through Friday in Australia. Oops, make that go a little bit further. On these days, people are using more electricity. You can see when it's really hot on this blue day, there was a lot of heat wave and everyone was using electricity to cool their homes. But the main pattern here is the weekday pattern. So what you can see here is people going to work in the morning, having a lunch break, and then going home. You see this M-shaped pattern. And generally, the electricity is much higher than on weekends. See that difference in electricity usage during the day? So on working days, people use more electricity, and on weekends, people don't use as much electricity. What I really like to see here is Sunday. I think Sunday is really fun. So some people work on Saturday. Historically, people don't work as much on Sunday. And look how the shape of the pattern is very different from the 9 a.m. and 5 p.m. peaks. And this is because people sleep in. People really like to have a late start to the day on Sunday. Maybe on Friday night, Saturday morning, people are up late, starting the day early. Who knows? But on Sunday, people start their day really late. And we don't have that big peak that we see in weekdays, working days. So I think that's really fun to see. But when we come to modeling this, we probably want to include an annual seasonal pattern and a weekly seasonal pattern, which we could use the day of the week to represent. But you can also see in this plot a daily pattern. If I break up the data day by day, you can see people don't use electricity when they're sleeping. Sorry, I'll write that better. Sleep. But they do use electricity when they're awake, of course. So if I instead plot this as a daily seasonality, see that I've switched it over to period equals day, I now get a much clearer view of the peaks and troughs throughout the day. So when do people use the least electricity on average during the day? Yeah, exactly. So here's 6 a.m., here's midnight, right about here, 4 a.m. So 4 a.m. seems to be the middle of the night in terms of when people sleep, but broadly speaking, any time between 2 a.m. and 6 a.m., people use less electricity. And people start to wake up at 6 a.m., but most people in Australia wake up at like perhaps 8 a.m. So what is the peaks in this time series? It depends day to day. You wouldn't want to look at these less dense lines. These are just outliers. These are the heat waves. But generally, looking through the bulk of the data, When do people use most electricity? Yep, you've all got the right idea. So in the morning when they get ready to work at like 7 till 8 a.m. and then when they come home from work at 6 p.m. This is when Australians or Victorians use most electricity during the day. So you can see, just with a few different plots, we can get a very detailed understanding of what people do. There's a lot of information in this data set, and there's a lot of things that we want to include in our model to forecast demand accurately. And going back to one of the questions in the first session, why do we want to forecast this? Well, we want to forecast the amount of electricity people need so that we can produce enough electricity to meet the demand. If we didn't make enough electricity, then power would go out and people wouldn't be able to use their heating or cooling or cooking or all of the important things that people need. So we want to make sure we produce enough electricity to meet the demand, but we also don't want to make too much electricity. There's no point making this much electricity during the middle of the night, because then we're going to waste it all. But if I made this much electricity, people get upset because suddenly their electricity stops working. So it's really important to not only forecast the amount of electricity demanded every month or every year, but also every minute. And this daily or sub-daily seasonality is a really important part of understanding how people use electricity. Okay, so there's two ways in which we can visualize seasonality. Most often we'd use the seasonal plot, and this is the simplest to understand. But there's a seasonal sub-series plot which also shows some useful things about seasonality. In particular, while the season plot allowed us to see the peaks, the maximum, or the troughs, the minimum, the seasonal sub-series plot, which you can use sub-series, the GG_sub-series function to look at, allows you to see changes in seasonality. Now, it's a bit tricky to understand this one, so it might take a little time for you to look at. But here is the beer data set. And immediately you can see that the plot looks very different. Here we have quarter 1, 2, 3, and 4 making different plots. We call these sub-series. They're time series, but they're part of the time series. This is only quarter 1. So it's quarter 1 of 1990, quarter 1 of 1991, 92, all connected in a line. The second facet here is all of the quarter 2s connected into a time series. So quarter 2 in 1990, quarter 2 1991, quarter 2 1992, and we make a line out of that. And we repeat. The blue lines here are perhaps the easiest to understand. These are the average, the mean. So this is a convenient way to say, on average, quarter 4 had more beer production. You can see the blue line, the average, is exactly 500. Well, very close to 500. So you can see in quarter 4, Australia produced on average 500 units of beer every quarter. Whereas in quarter 2, you correctly identified earlier, is the minimum, producing just under 400 units of beer. But that's, if you just look at the blue line, you're not seeing the whole picture. What we're really interested in is the change in the seasonal pattern, the black line. And in this case, quarter 1 is completely flat, right? There's no trend in quarter 1. Quarter 2 also doesn't have a trend. It's flat. Quarter 3, no trend. But if you look at quarter 4, See how it's decreasing? What does this mean for my seasonal pattern? My seasonal pattern is normally a repeating pattern going up and down with a constant time between it. But the shape of this seasonality might change over time. In this case, Q3, Q2, I'm not drawing that very well. This is Q4, Q1, Q2 is the minimum, Q3, 4. 1, 2, 3, 4. Okay, so this would be if the seasonality is the same and doesn't change over time. But we can see that Q4 is actually decreasing. So actually what's happening is that the peaks are getting smaller. Q4, Q4, Q4. And this can look like there's an overall downward trend, but that's not the case. The other seasonal periods, like Q2, is staying the same. Q1 is staying the same. Q3 is staying the same. It's only Q4 which is decreasing. So if I go back to the original plot of the data and look at this again, now if I look at the minimum, it stays roughly the same. If I draw that a bit better, the minimum usually stays pretty close to 400. But the maximum started at 550 and it's been decreasing. Now it's a bit under 500. It's maybe 475 like we saw before. So the sub-series plot allows you to see if the shape of the seasonality is changing over time. It's a bit tricky to see, it's a very subtle difference, but looking at this time plot, you wouldn't be able to identify that very easily. You might see, okay, maybe the overall variation is shrinking, maybe there's a downward trend, downward trend. But if you said there was a downward trend, that wouldn't be exactly right. It's really just Q4 decreasing and the other quarters are staying roughly the same. So the sub-series plot allows you to see that. Now, most of the time, the seasonality is a consistent pattern, and therefore the sub-series won't show any differences. Normally, the seasonality doesn't change over time, but it's a good plot to use to check that the seasonality is stable. Again, when it comes to modeling, some time series models are able to capture seasonality and trends changing over time, whereas other models require or assume the seasonality to be constant over time, not changing. And if you find that your data set changes seasonality, like in this example, that would affect the model that you choose to use for forecasting this time series. Because in the future, you might expect Q1 to continue to be flat, Q2 to continue to be flat, Q3, but for Q4, you'd want to forecast a decrease. Okay, so I'm going to put this code in the chat, and I want you to try out those season plot functions for yourself. This is the number of people traveling to Australia for a holiday. Maybe someone can put this in the Q&A as well for me, if it's perhaps useful for other people to copy from Q&A. So this code will allow you to create a Sybil, a time series with the number of holidays by each state. So all of the different states in Australia and the number of people coming for holiday purposes. And I want you to use the GG functions. So we'll use GG season and GG sub-series in order to tell me what the peak seasonality is and the trough of seasonality for this data set is. And while you work on that, I'll answer some questions. So one of the questions is, it looks like the key variables are categorical, and that's right. So often key variables are text values. In this case, it's a character vector. You might also find that they're factors, categorical variables. And that's because text is useful for identifying or describing something. So most often you'll see key variables are characters. Okay, so the first one here, first of all, looking at this plot, this time series, we should try an auto plot just to get an overview of the data set. I will try to keep the code on screen for as long as I can to help you copy it down if you're having trouble copying it. So you can see in this data set, most of the time series don't appear to have much trend. Perhaps in Victoria, where I'm from, this purple line starts flat, but has an increasing trend towards the end. A few different time series have that in this data set. But the biggest feature here is the seasonality. You see that repeating up and down pattern? And that is because it's holiday travel. So people like to come visit for a holiday when the weather is nice and don't want to come when it's cold. You can get the data for this exercise, holidays. It's from the tourism dataset, which is included in the FPP3 package. So if you write library FPP3, that should work. And we've done some changes to manipulate the data and summarize it. Okay, I'll answer the question. Here's the code for the next plot, GG season. I want you to have a look at the different seasonalities in each state. Do they all line up? Are some having peaks at different times of the year? Okay, and another question, does the index variable have to be a day, week frequency before plotting to GG season, day, week? Yes, so you do need a Sybil object. So if you have a Sybil for your dataset, like I have here for holidays, then you can use a season, GG season. But in order to create the Sybil, you'll need a valid index, in this case, quarterly frequency. If I have an annual time series, like perhaps Oz economy, global economy, and I try to compute a GG season on GDP, it won't let you because this is an annual time series every 1 year, and therefore there's no seasonality in this time series. Okay, here is the season plot. I'll copy the code for you that we've done so far. And this gives you a nice overview of each of the different states. It gives you a little season plot for each one. Which state has a peak in Q3? It's a bit hard to see, actually. Maybe that's a bad question. Maybe I can zoom out a bit. No. Yeah, you probably need to know Australia a bit better. There we go. I will make sure you can still see the code. There's the plot with all the labels. So yes, very quickly you can see in each of these states that in Q3 the maximum is in Northern Territory, and in fact Queensland as well. The reason for this is because Northern Territory and Queensland, if I bring up my map of Australia again, which looks a bit like this, Northern Territory and Queensland are here. And this is closer to the equator. So it's nice and warm in winter. So all of the other people in cold Tasmania, everyone in Victoria, all fly up to Queensland and Northern Territory to enjoy a nice holiday. And people coming to Australia definitely don't want to come to Tasmania, where it's really, really cold. Instead, for Tasmania, when do people like to come to Tasmania for a holiday? That's right. So most people come to Tasmania in Q1, which is summer. It's the middle of summer, the hottest time of the year. And so because Tasmania is such a cold place, people only really want to go there for a holiday in summer. So even though you've got multiple different places, multiple different time series in this data set, being able to see all of them on the same plot and compare their seasonalities can see some interesting differences between the seasonality in each state. So you can see in hot places like Northern Territory and Queensland, people like to go there when it's cold in winter. Whereas in Tasmania and Victoria, where it's cold, people like to go in summer when it's comfortable. Okay, so now we've seen 8 different plots altogether. When we do a sub-series plot to see if there were any changes over time, give it a moment. Dennis, with your error here, found format, you might need to update your packages. So I suggest that you install perhaps the feasts package again. Try this one out. So if you're getting a similar error, object found format not found, that could be because the ggplot package is new and the feasts package is old. Try installing it again. Okay, so here is the sub-series plot. I've got a whole grid of different plots now, so it takes a bit of thinking to see how it works, but just like the last plot, in the rows here we have the countries, or the states, I should say. And just like the sub-series plots we saw before, on the columns of the facets, we have each quarter. Now, it'll take some looking, but is there any changes in the seasonal pattern for some of the states? This is also a useful plot to look for any anomalies, any strange observations in the data. You can see in Queensland here, most of the quarters are pretty flat, if not increasing a little bit. But in Q1, there's something strange going on. There's this drop that happened over a couple of years. You can also see in the ACT, our capital territory, Q1 was slightly increasing, Q2 was flat, Q3 flat, but Q4 has changed a lot over the past. It started by decreasing, then flat, and then increasing. So the Q4 in ACT has been changing a lot more than other quarters. But overall, the patterns, the shapes of each of these lines look very similar state by state. So it doesn't seem to have a very strong change in the seasonality over time. This is one that I suggest that you work through with your mentors quite closely. It can take some time to fully understand how to interpret this plot. Okay, so that's everything that we've just seen. Now, another one that I will just show you here, because it's not something I use very often, but it's useful to know that it exists and have the code in case you wanted to try it out for yourself later on, is to use a calendar to visualize the data. Now, it looks like this. The code for it is here. It's a bit complicated to get involved today, but essentially we prepare the data as a calendar using frame calendar. And then we use some direct ggplot code to make the plot, and then we improve the style of it to make it look better. Now, there's an easier function to use called facet calendar, which works just like any other facet function, but with time. And this is a useful way of plotting sub-daily data. So the electricity demand that we saw every minute, for example. In this case, we're plotting that data exactly, actually, Victorian electricity. And so this is a nice overview of the year of electricity demand in Australia or Victoria. And you can see on the New Year's, where it was a holiday, even though it was the middle of the week, there wasn't much electricity used. And people only started going back to work at the end of the second week of the year. So this is a good overview of holiday effects in the data. Okay, so now we have a good understanding of seasonality. We're going to play a little bit of a quiz. Seasonality or cyclical patterns, I think. Do I have that quiz? Yes. So we talked about this before. A seasonal pattern has a fixed pattern and it's consistent. So it's always quarters of the year, months of the year, days of the week. It's always this natural repeating pattern. Whereas cyclical patterns are not of a fixed period, so they're inconsistent. That's the main difference. So here's that summarized. Seasonal patterns have constant length, cyclical patterns have variable lengths. The average length of cycles are more than a year, which is longer than seasonal patterns. And the shape of the cycles change more than seasonal patterns. So I want you to put in the chat. Unfortunately, it looks like Bahman was only able to make polls. No, I can make a poll. Okay. Can I make a new poll? Let's see. I'm not sure I can do this. Yeah, I'll have to sign in. I won't be able to set up a poll. So you'll have to put it in the chat. Is this seasonal or is this cyclical? What do you think? Or both. You can also say both. So here we have the Australian electricity production, but it's been added up to be every quarter. So this is quarterly data. You can see this repeating pattern. Is it repeating consistently like seasonality, or is it irregular and quite random like cyclical patterns? Okay, it seems like most of you have the idea. There's most people saying seasonal. Some people are saying both. Some people are saying cyclical. There's definitely a trend, but that's not the question. Now, this one, the correct answer is seasonality. It is a seasonal pattern, and it's seasonal because it's a consistent period of time and a consistent shape for each repeating up and down pattern. So these are always 1 year apart. So this is seasonal. Now, you could argue that there's a bit of cyclical patterns in here as well, like maybe there's a flattening here and a flattening here, but it's such a subtle detail that I'm looking for the overall pattern in this data set, the most dominant pattern. So this is seasonal. And is it additive or multiplicative? I would say this one's additive. It's a pretty constant fluctuation, even though we have this increasing trend. So I'd say this is additive seasonality. Okay, next one. Australian clay brick production. Is this additive seasonality, multiplicative seasonality, cyclical, or both? Okay, very good. Most people are saying both. That is the correct answer. So you can see on this small pattern here, the up and down, every year, 1 year apart, we have seasonality. Now this seasonality starts with a very small fluctuation and it gets a bit bigger. So I would say this is multiplicative seasonality. But we also have in this time series a cyclical pattern. It goes up, sharply drops. Now it's not always that shape, but in this case, it goes up, drops a lot, increases, drops, increases, drops, increases, drops. And now it's increasing. What do you think is going to happen next when we forecast? At some point, it's probably going to drop down again and then increase again. We don't know when that will happen. It's very hard to predict, but this is a cyclical pattern. So in this case, we have cyclical patterns and multiplicative seasonality. So we have both. So good work, everybody. It seems most of you have gotten the right answer for that one. What about this one? Seasonal, cyclical, or both? Okay, a bit more variation here. Some people saying seasonal, others saying cyclical. I think most people are going with seasonal. And I agree that the most dominant pattern here is the seasonality. So you can see that these patterns are seasonal. But you can also see retail employment. We've got this increase, drop, increase, drop, increase, drop, increase, and it's starting to drop. So this actually has both seasonality and cyclical patterns. And this looks fairly additive. So the seasonality appears to be additive because the shape, the variation here is similar throughout the entire time series. And I'm going to skip that one for time. What about this one? The annual Canadian lynx trappings. Is this seasonal, cyclical, or both? Okay, a bit of mixed opinions. Some people thinking both. I can only see one pattern here. Whether it's seasonal or cyclical is a different question. Seems a few people are saying seasonal, but most people are saying cyclical. So I think most people have the right idea. This is cyclical. This is a classic cyclical example. In fact, it's a predator-prey relationship, and that's why it's cyclical. There's a few reasons why it's cyclical. The first reason, you look at the gap between the peaks, or gap between the patterns in general. In this case, this gap here is shorter than this gap. This one might be 8 years, this one's 10 years. The gap between the next one looks more like 9 years. And then maybe 9 years again, a long one. It doesn't look that long, actually. Maybe 9 again. This is just doing it by eye. This might be 11 years. A short one, 8 years. The amount of time between the patterns changes. So that's one reason why it's cyclical. The other reason why it's cyclical is because the shape isn't predictable. The amplitude is not predictable. See how the peak is this height, then this height, then this height. What happens next? We know it's going up, but is it going to stop here and immediately turn around? Is it going to keep going up and turn around here? Is it going to go up and turn there? It's hard to tell. And that's another reason why it's cyclical. The shape of the pattern is changing every time. So it's not a consistent pattern, and therefore, with a difference in time period between the pattern, it is a cyclical pattern. So that's that summary of differences again. For that last example, the seasonal pattern had a constant length, but we saw that that one had a variable length, and the magnitude was more variable as well. One thing we didn't look at was the length of the cycle. So the other big clue there, excuse me, is that this is years. This isn't time in year, and the patterns are repeating every 9 to 11 years. There's not many things natural that repeat every 9 years or 10 years exactly, like temperature or something. So this is a cyclical pattern, is the other clue for that. Okay, so the last type of plot that we'll look at in the final 10 minutes of today, and we've got 10 minutes left, I think. Let me check that. Yes, 10 more minutes, is lag plots and autocorrelations. Now, lag plots are not very useful plots. I never use them in practice, but I use an autocorrelation plot, an ACF, you might have heard of it before, all the time. ACF is perhaps my most used plot for modeling. But we are going to look at lag plots briefly because they help us understand what an autocorrelation is. So here's Australian production. It's a data set, it's a Sybil, quarterly data. These details don't matter so much. But a lag plot, just like we did season plots and sub-series plots, we use GG_lag. Now, if I look at each of these plots, what can I see? It looks like a scatter plot, but I've connected time with lines. If I use a point geometry, it is essentially a scatter plot. But the point of a lag plot is to look at correlations. So hopefully everyone's familiar with correlations. If it's along the diagonal, like this, the correlation might be high. You might have seen the letter R before. This might be 0.8. If it's in the off diagonal, maybe this is a negative 0.7. It's a little bit more spread out. So for each of these plots, lag 1, we are showing beer, the data set y on the y-axis, and the lag 1 of y, so that's yt minus 1, on the x-axis. So the amount of beer produced this quarter compared to the amount of beer produced last quarter. So you can see in quarter 4, we're currently producing a lot of beer, but in quarter 3, the previous quarter, we didn't produce much at all. So that's how this plot is laid out. But what's most interesting about this is the correlation. So what's the correlation of this first plot? Just have a guess. You don't need to know, be precise. You can put some suggestions in the chat. To me, it looks like it's going downwards a little bit. It's pretty spread out. So the correlation will be equal to what? Okay, it seems like that might be a tricky question. While you think about it and write it in the chat, I'm going to answer a couple of questions. So this first question, is the data from the Olympics, which was every 4 years, inherently cyclical? No, just because it's every 4 years doesn't guarantee that it has a cyclical pattern. In this case, the Olympics doesn't have any seasonal or cyclical patterns. And to answer your other suggestion, negative correlation. Yes, I think this is a negative correlation. It's non-linear, but correlations are linear metrics, but it's really spread out. So this might be perhaps a negative 0.3. So I'm going to put my correlations, my R, on this plot. So this is negative 0.3. What about this second lag? Now it is closer together, but it's still negative. So maybe this is negative 0.6. And I'm just going to add each of these correlations to the plot on the right. Lag 3, some of it's going up, some of it's going down. I think it all cancels out, and overall it's pretty nothing. So I'm going to say the correlation here just visually is maybe negative 0.1. But something really interesting happens at lag 4. This is yt minus 4 now on the x-axis and yt on the y-axis. See how it's all lined up in a line? The correlation for this is going to be really high, 0.8. So it's going to actually be really positive. The reason for this is in yellow here we have all of quarter 4. What is quarter 4 minus 4 quarters? Quarter 4 lag 4. It's going to be beer production in quarter 4 of 1 year compared to last year's beer production. And therefore, we have a very strong positive relationship, a similarity in the data from this year and last year when we match up the quarters. And repeating, we have a negative correlation, negative, 0, positive. So putting it all together, it looks like this. You can see that there's this pattern emerging in the correlations. So almost always we don't look at the lag plot. Instead, we use what's known as an ACF plot. And that's what I've drawn here. But it's the same idea. We plot correlations, we calculate, we plot scatter plots between yt and lag of yt, calculate correlations, and we summarize all that information with just one vertical line. So here's the math behind it, how we calculate the correlations, just roughly. And to calculate these autocorrelations in R, we use the ACF function. So just like we did GG underscore season, and we told it what variable we're plotting, to calculate the ACF, we use the ACF function and show what column we're calculating ACF of. And here's those correlations calculated exactly. So we had a slight negative value that we saw before, a strong negative value, a very weak negative value, followed by a very strong autocorrelation at lag 4. So we see when it lines up, also in quarter 8, we get a very strong peak. But of course, looking at a table isn't very useful. So most of the time, we will autoplot the ACF. So if I take the results of ACF and pipe it into autoplot, I get this ACF plot. And you can see that shape that I drew out before much clearer. Now, to choose the lag, you want to choose something long enough to see all of the patterns. In this case, I would probably choose something longer, like 4 years, which would be 16 quarters. Maybe I've got a plot of that. Yeah, here we go. So the default is usually good enough. So if you don't specify lag max at all, it will choose something appropriate based on the data. In this case, it's chosen 18. And this is enough to see at lag 4, 8, 12, and 16, we have peaks. So this is to see we have seasonality. Now, because everything is centered around 0, this says we have no trend. But you can actually see all of the interesting features from an ACF plot that we could see in the other plots. So now I'm going to show holidays that we were looking at before. We calculate the ACF, and then we plot it. Now, in this case, we knew that Northern Territory was very seasonal. When it was hot, people didn't go, but in winter they went. And in Tasmania, people went when it was cold. But the ACF plots that all the same. The peaks every 4 quarters are now lined up. So it doesn't tell you anything about when the peak is and when the trough is. It just tells you that the seasonality exists. And these blue dashed lines are corresponding to a unit root test, not a unit root test, sorry, a hypothesis test, saying if it has significant seasonality or not. So with an ACF plot, we're able to see trend, seasonality, and even more subtle patterns. So if we have trend, it'll be a slow decay. It'll look like this, all positive, slowly decreasing. If it's seasonal, we'll have autocorrelations bigger at seasonalities. So that's that lag 4 peak that we saw here for quarterly data. This is seasonality. So what happens when we put them together? Here we have trend and seasonality. And when I plot them together, you can see the dominant feature here was the trend. Most of this pattern is the increasing trend. And so all of the data is slowly decreasing when we show it with an ACF. But what you can see at lag 12, 24, 36, and 48, this is the seasonality. You can see this slight little bump. See that scallop? It kind of increases just a little bit at lags 12, 24, 36, and 48. And this is my seasonality. And because it's such a small bump, suggests that there's not a very strong seasonality compared to the trend. This is the trend. So just like the other plots that we're seeing, the sub-series plot, it takes some practice to get familiar with. So with your mentors next week, I recommend that you try this out some more. There's also more exercises in the textbook that you can work through. Of course, you've also got stock price. Now, this doesn't necessarily have a trend, but it has a similarity with the previous day. And that's why we get the slow decay, but it doesn't stay positive for as long. So another quiz, perhaps we'll run at 5 minutes over, apologies. So if you have to leave, I understand. But which is which? So A, B, C, D, each of these match up with one of the time plots in the top row. The first one we have here is the daily temperature of a cow. So this is measurements of temperature, internal temperature of the cow. And you can see it's been slightly decreasing a little bit, but it's very random. So in the chat, A, B, C, or D, which of these ACFs do you think corresponds to this weak decreasing trend with a lot of randomness? Okay, most people are going with D, but the correct answer here, I saw a couple of people get the correct answer. The correct answer in this case is B. The reason for this is because we have the positive values decaying slowly. They're all positive, but compared to D, which most people thought it was, This has a very strong decreasing pattern, whereas the trend here is quite weak, and the noise, the randomness, is much stronger than the trend. So B represents a weak trend. So B is the correct answer. What about plot 2, monthly accidental deaths? This one has a seasonal pattern and not a lot of trend. A, B, C, or D, which one matches 2? Okay, a lot of people said A, and now a lot of people are saying D. The correct answer was A. These ones line up. The reason why is because you can see at lag 12, the seasonal lag, there is a very strong peak. So this says seasonality, and it also tells you how often that seasonal pattern repeats. In this case, every 12 observations. For monthly data, that's 12 months of the year, or every year. This has an annual seasonal pattern. Why isn't it D? Well, D has a trend. D has this slow decay. So because series 2, plot 2, doesn't have any trend, it is not D. Okay, last question. Plot 3, monthly air passengers. Is it C or D? 50-50 chance, you can guess. Okay, everyone's very confident with this one, answering so quickly. Almost all of you are correct. It is in fact D. In this case, we have the trend, we have the seasonality. All of these patterns are very, very strong, very clear. There's not much randomness. And D has a slow decay for the trend, and it has the little peak at 12 for the monthly air passengers, the monthly seasonality. So 3 is D, which leaves the annual mink trapping, the last one, to be C. The reason why C is lined up with annual mink trapping and not monthly accidental deaths is because this is a cyclical ACF. So ACF is very useful for identifying the difference between seasons and cycles. You can see the mink trappings, the peaks are every 9 to 10 years. See how the peak in this ACF here isn't very specific to 10? It's either 9 or 10, whereas the seasonal one was very exact. It's definitely 12. And this is because this pattern, the spacing between them is sometimes 9 years, other times 10 years. So this inconsistency results in a smoother ACF. Okay, so hopefully you found that valuable, especially for telling the difference between seasons and cycles. The last type of ACF, which is incredibly useful for the later sessions, is white noise. White noise is completely random data. So if you've used R before, this is random data from a normal distribution. And I've just plotted this over time. So this doesn't have any trend. There's no trend. There's no seasonality. There's no cycles. There's nothing. This is all random. And the ACF plot is really useful to see that. See how there's nothing significant in this plot? There's maybe one outside the line, but this is a 95% area. And I've shown 15 lags, so maybe one of them is out just by chance. There's nothing really strongly outside the correlations. So in later weeks, when we look at modeling, we'll be hoping that the residuals from our model, everything left over, doesn't have any correlation. We'll want it to be white noise when we do our modeling. We'll get more practice at looking at that in future weeks. So here's an example of a data set, a time series, number of pigs slaughtered for meat in Australia, in Victoria. And the ACF appears to be white noise. This doesn't have any patterns. It doesn't have the slow decay of positive values that you might see for trend. It does, actually, maybe it isn't white noise. You can see this peak here. Is this by chance? This isn't by chance because it lines up with 12. And 12 is special because it's monthly data. So this is 1 year. So this suggests that we have very weak seasonality in this data set, even though in the previous plot, it wasn't very obvious. It's not very easy to see if there's a seasonal pattern here, but the ACF has revealed a very subtle, weak seasonal pattern at lag 12. So therefore, we have some slight seasonality for lag 12, and it's not white noise. Okay, that's all I have time for today. I will stick around for a few extra minutes to answer any last questions that you might have. But thank you all for coming today. You've been excellent. I really appreciate you participating in the chat, asking questions. It's been great to teach you all today, and have a great rest of your day, and I'll see you all tomorrow for a bit of modeling and more plotting. Thank you, everybody. Okay, one question. I'll pause the recording now, or finish the recording.